All right, welcome everybody to the next New York Combinatorics seminar. Today we'll have Amanda Redlich, who's going to tell us about squares.
Hi, folks. So Deepak had a chance to practice, but I assume I'm also in the right location with the right volume level. Good? And you guys, okay. Well, thank you so much for the invitation. I'm really happy to be here. I feel like this kind of wide-eyed out of towner. I got off the train and people started asking me to give donations for things. It's exciting to be in New York, and it's exciting to be with you guys and talking about this project, which is super fun. It's about C4 is a square, but actually it turns out other graphs are also squares that are not even C4. And so this is a sort of line of investigation that I've been working on off and on for a year or two. So all kinds of folks have been involved. So earlier work was with Annie Raymond, who's at UMass Amherst, and Pranav Garg, who was a student there at the time, and I think he's gone off into the world of business. And then the next chunk of work I've been doing with a group that formed at AIM last summer. So Karen Collins, David Galvin, Christine Kelley, and Emily McMillon, who is on the job market and is wrapping up her postdoc and is amazing. My name is Amanda Redlich. I'm at UMass Lowell. So I'm not too far away. If you guys want to come visit, feel free. And it's October 3rd. Right? Yeah, okay. So I'm told that if my mouse, do I just hit?
Does it work?
No.
Okay, then move the depends.
Where's the mouse? Is it pretend to the left or pretend to the, oh, it's pretend to the left. Okay. Ha! Okay, so what I wanted to start informing you is that C4 is actually a square. I made this image and then I realized I didn't measure it, so it may not be a square in this image. So this is the sense that I think we're all on board with. But actually what I want to talk about today is treating graphs as things that can be multiplied together. And so it's a square in the sense that like 9 is a square because 9 is 3 squared. So just like in numbers, you can be like, it's 8 is square, 2 root 2 is the square root of 8, but it's not really what we mean. So too in graphs, you can start thinking about, okay, but if I want to classify stuff as like really square, how do I do that? What traits do I look for? What does it mean for a graph to be a square? So this is my first example because it cracks us all up. That's good. Why? So a lot of this stuff grew out of something that other folks did earlier. So there's a very interesting and theory-heavy paper from 2018 by Gregory Blekherman, Andy Raymond, who's the same Raymond, Reka Thomas, and Singh. I am blanking on the first name of. The only one of these people I have met is Annie. But in 2018, they came out with this paper about using the gluing algebra of graphs to understand homomorphism density conjectures. And so there's all kinds of interesting stuff about how this particular graph algebra connects to homomorphisms. And here's lemma 2.8. So this is the meaning of square that I'm going to be using in the talk, this definition right here. An unlabeled connected graph G, okay, check, is a non-trivial square, i.e. G equals square bracket, F squared, square bracket, for some partially labeled graph F that is not a fully labeled copy of G, if and only if there is an automorphism phi of G such that phi is an involution, phi fixed is a non-empty proper subset of the vertices of G and the vertices, okay. So this is very true and very useful for what they were working on in their paper. And Annie thought I would be interested too, and she told me about it. And I looked at it and said, that is very interesting. What is, like, can you draw one, though? Because this is a very abstract, there exists an involution with algebraic properties. And they weren't particularly interested in drawing them, that their work was going in another direction. I thought, well, I want to actually build one with my hands. And so the point of this talk is going to be about, well, how can we go from the sort of theory side to like, let's actually use some graph structure properties and think about building a graph for real. And I believe that's what the next slide is going to be. Let's see. Okay, so in this gluing algebra of graphs, which there's a fair amount of history on, this is how you multiply stuff together. So you can read the textbook by Lovas, or you can just look at this picture. So the idea is I've got two graphs. So there's G1 and G2, you see in the first example. And some of the vertices are labeled so we color coded them and I also have numbers on them. So they're like really for real labeled. And your rule for multiplying two graphs together is you're going to identify the vertices that have the same label. So the one gets glued onto the one, the two gets glued onto the two. If you've got like an extra leftover label, don't sweat it. Just let it be its own thing. And if you've got something that's not labeled, again, don't sweat it. Just let it be its own thing. So if I multiply G1 and G2, my result is going to be G1, G2 on the other side. So we're really just gluing stuff together. It's not super fancy. We're not going to have double edges. We're not going to worry about compatibility of labelings. We're just doing what we can. You feel okay about equation A?
That really depends on marking of.
Exactly. So the labeling is very important. So two different graphs could have several different products depending on which guys I glued to which guys.
This name.
This is the gluing algebra of graphs. There's a book by Lovas that I'm blanking on, but if you want, I can give you the reference afterwards where it kind of nails it down.
Is it different from just a piece where you're sticking two graphs together across an edge that you flag?
Because there's more flexibility. And what that 2018 paper talks about is you can do like a whole polynomial and have that be meaningful. So that's the second example here. So we're also going to add graphs, subtract graphs, have coefficients, linear combination, like the whole schmear. So in the second one, I'm going to square an edge minus an edge, where one of the edges has one labeled vertex and one of them doesn't. And so we're going to FOIL it just like you did in algebra class. So one labeled edge times one labeled edge. Well, that'll give you this. Oh, I guess I can't point. Oh, I'll point with my shadow. There. So this guy here is the square of the first term in parentheses. We're okay with that? Okay. Then we minus 2 times both of them because that's how the difference squares works. Okay, so we've got minus 2. And then both these guys together, well, there's no matching labels, right? This one has a label, this one doesn't, so nothing happens. I'm just going to write them next to each other. So minus 2 disjoint edges. And then what about the square of the last guy? He doesn't have any labels, so nothing's going to happen if I multiply him by himself. He's just standing foolishly next to each other like this. And we're allowed to group like terms and all that stuff because we're in polynomial world with graphs. So I subtract 2 of them, but then I add one of them back, group like terms, and I get this at the end. Yes.
So, for adding, labeling.
Doesn't matter. So adding means you just write them next to each other. So it's the disjoint union of the graphs. Multiplying means you identify labels if whatever labels you could reasonably identify, you do. And everything else just kind of chills. Yeah.
Question, if you have to have a consistent graph between those labeled vertices, if you're multiplying, is that right? So like, if the right hand graph did not have an edge between it.
You do like the union or like the Boolean union or something. So if there was an edge between 1 and 2 in one graph, but not in the other, that edge exists in the product. So you put as much stuff as you can.
A second definition question. Sorry, I don't know if is someone still talking in the room.
Someone had a question about the double
sorry.
brackets. Maybe that's your question as well.
No,
Okay.
I'll ask after. It's fine.
Okay. I really wanted someone to ask that question, so I'm thrilled. Thank you. So what you'll notice in the first example, which is the one that's like more definitive, I guess, the colors and the numbers all stayed on the other side, right? But this guy has no colors or numbers on it. What I actually want to do is think about, is there some way that I could do like colors and numbers and stuff so I would get a graph isomorphic to what I'm really looking for? So the notation that was developed in that 2018 paper is if you put 2 square brackets around, it means after you do all the algebra, take all the labels off. So it looks anonymous again. And so you can see like there's a 1 there, there's, that vertex is labeled 1, vertex is labeled 1. Then we erase all the labels and we collapse it. So this is the correct formal notation that is used in a lot of the published papers. But for the questions I'm interested in, it's kind of a nuisance. And so I'm not going to be using it as much. But if you have any confusion, I can write things in a more formal notation way. Sure.
I wonder if the second following is actually one direction. There can be multiplication.
That's correct. So that's exactly right. So one of the things that's really interesting about this is when we factor a polynomial in like normal world, there's only one way to factor it. When you factor a graph, arbitrarily many ways. There's not even a unique square root. There's not even a unique square root up to sign a lot of the time. Some graphs have properties where they can be factored uniquely. A lot of them don't. So it's a two-way inequality, but it's kind of among equivalence classes or something. I don't know how to wrap your head around it, but yes, this is a specific way to derive that graph, but there are many other ways that you could if you wanted. And then someone else had a question, but I think he also just left the Zoom.
No, I'm
Okay.
still here. It was
Oh, good.
just,
Hello.
no, you actually answered it with the double brackets thing. The question I was asking was about what the notation. Well,
Oh,
sorry, the
great.
labelings
Thank you.
disappear.
Yeah,
Is that consistent with like we can't stack operations in the algebra in that sense? But never mind. You're saying it's
probably.
the
Yeah.
information is deleted by the double brackets,
Yes.
which is
Yes,
effectively
that's
asking the same
correct.
question. Thank you.
That's correct. So I'm coming at this from sort of a structural graph theory perspective. Many of the other folks working on this are coming at it from a homomorphism perspective or from an algebra perspective. So the part that's interesting to them is not the part that's interesting to me. And I think that's where the notation kind of collides.
Gotcha.
So do we all feel like we can multiply graphs? Okay. Well, I got one shrug, but everyone else was looking confident. So, all right, how to square. So what you square is you multiply the same thing times itself. That's the whole deal. So if I have a triangle with 1 and 2 and I multiply it by its own self, then at the end I have two triangles that are glued together on an edge. So those two edges just kind of superimposed and became one. So when I'm talking about a graph that's a square, what I mean is I can find two copies of some graph that if I multiply them together, I'll get the thing I actually want. And so the subtlety here is that what I'm actually going to do, as Zoom audience member ably pointed out, is I'm going to start with something that has no labels at all. So I don't have a hint about, where do I put the labels or where do I cut up the graph? And I still want to find some way to do this. And that becomes more and more challenging. All right, we're all on board. We're all on board. Okay, so the title of the talk, I think, is the next slide. Yes. Okay, so is this a square? Could we somehow label something or other to get something that if we square it, we get a graph? Yes? Anyone want to volunteer? Suggestive coloring right here. So what you can do is just take like an L. Look at that. If I took this guy and multiplied it by itself, so I did color coding. So I'm going to pretend like reds have to match to the other copy of the red, but the black doesn't, then they're just going to kind of tag along and I'll get this. So there's an L, there's another L, Zoom people. So there's one L that's kind of going up and across and another L going down and right. There's two copies of the same graph and they're identified at a couple of special vertices in exactly the same way. That's how I know it's a square.
So you can glue at vertices.
Yes, I can glue at vertices without edges. I can glue at vertices with edges. It's very flexible. But the questions we're going to be asked are ones where it's like, you don't have a clue, what kind of gluing to look for. How do you start from scratch? So going backwards, we all know this is a lot harder than going forward. So multiplying things together, but dividing or finding a square root is real challenging.
And could I ask one?
Oh, of course, yes.
So what if there's a two-sum operation where you stick it at an edge and then remove the edge?
Mm.
So you could take two triangles and stick
Yeah.
it at an edge and then remove the edge and you get this.
Yeah, that's very interesting. So I really have only looked at this particular rule for combining graphs, but I imagine you could ask the same question with sort of any mode of combining graphs that you want and still be curious if it's a square or not. I'm now cranking. We should talk when you're able to talk. I'm very curious about that. Other potential research papers.
Yeah, I have a question.
Yes.
What if there are two vertices with the same label, that are not symmetric,
So then
and you multiply it by another graph with two vertices with the same label?
So you mean within like
So-
the original factor, there's the same label appearing twice?
Yeah, yeah.
Okay, so we say that's not allowed. That's how we deal with it. I don't know. I imagine to be logically consistent, you would probably identify within each factor the two matching labels and
Oh. But
multiply.
in this example, you have the two red
Oh, that
labels.
was that's because I was getting ahead of myself. I am sorry about that. So what I really want to indicate by the color coding is these guys are in the original graph getting glued, and the other guys are getting duplicated in the new graph.
I
Think
guess
that
so that the two
classification is
red
gonna be
labels, the two red vertices are going to be labeled
yeah.
differently.
Yes.
Okay,
Yes.
cool. Thanks.
Yeah. My co-authors and I had about a week of talking about what color to use and when to put things the same color, when to put them different colors. And you are convincing me now that Karen was right and that Emily was wrong. I'll get back to them on this. But also, I think this way of classifying vertices will make more sense as I go along a little bit. So I'm hoping that'll feel better. Yes.
Just one basic question about
Yeah.
multiplying. If you have a 1 and a 2 on one graph and a 1 and a 2 on one
Yeah.
another graph, and this one has an edge and this one doesn't,
Yeah.
are you allowed to multiply?
Yes, you are allowed to multiply. So as long as, so you always multiply two graphs, and what you do is you identify the intersection of the common labels with each other. So if this one has a 1, 2, and a 3, and this one only has a 1 and a 3, you identify the 1 and the 3, the 2 does its own thing, and the edges always come along. So if you have one with an edge and one without, in the result, it's an edge.
Okay.
Yeah. And I was wondering if I should do some chalkboard examples. Would a chalkboard example be handy for anybody, or we're all exampled out? All right. Oh, shoot. Now I got a thumbs up. Does that mean yes example or yes, I'm okay?
No.
Okay, no example. All right, great. Onward. So the next thing I want to talk about is butterflies. Look at this beautiful butterfly. So there's so many nice features of this butterfly, a native species, a pollinator, eats milkweed, great stuff. But what I want you to look at in this picture is that it's got a body in the middle and then it's got two wings that match each other. And it turns out square graphs are butterflies, that they have a body in the middle and then they have two wings that match each other. And this is a way of thinking about whether or not a graph is a square. Can I kind of draw it in this way? Can I visualize it by saying this chunk is its own chunk, and then these two are a right and left wing?
So, when you say that, is that like a characteristic theorem? So,
Yes.
it's clear. It's clearly it's clear that all squares, all graphs are sorry, all butterflies are squares.
Yes.
But
It's an if and only
is the
if.
converse? Is the converse? Oh, okay.
Yeah.
That's surprising. Okay.
Yeah. And it's one of these things where like initially you're like, oh, that's very deep, and then you think it through, maybe it's not so deep. So hopefully by the end of the talk, everyone will think it's not deep, because that'll mean you've understood the idea. So this is a photo of an actual butterfly, and then this is a cute example graph because it kind of looks like a butterfly. But also in graph world, you can see that it's got this sort of central body, and this is where the color coding comes in. So the black vertices don't really have a symmetric match, right? That's like the center body. And then the two tones of gray are the two identical halves. So this is when a graph is a butterfly, when I can kind of categorize the vertices in these three categories. One category that's the center, and then two isomorphic left and right parts of the graph. And then I wonder what the next slide is. Right. And so then here's the lemma. We've defined a thing called a butterfly involution and say it's a square. Now, what kind of involution is it? It's an involution where some of the vertices are mapped to their own selves. Those are like the body of the butterfly. And then the others are left ones mapped to the right and right ones mapped to the left. So it's an automorphism and it's an involution because if you go left, right, and then you go right, left again, you're back where you started. So that's the lemma, and it turns out this exactly characterizes squares because once you know this involution, you can find a square root, which I think is the next slide. Okay, so here's the square root of a butterfly. So basically it's the body and one of the two wings, right? This butterfly just happens to have its wings folded up. I didn't destroy a butterfly for this talk. But then here's a picture of a square root. So here's a butterfly, there's a body, there's a wing. I square it, it gets the other wing and the other antenna and the other dangly part on the bottom. Maybe that's the lower part of the wing, I don't know. but the body is staying fixed. So this was the notion of the color coding. So the black vertices are fixed. So you can imagine them as each having distinct labels. So they're not multiplied or anything. And then the gray vertices don't have any labels. So when I multiply it by itself, I get two copies of them, just like we saw with the square.
Couldn't you have removed one thing in the middle?
Indeed. Turns out you can do this a whole bunch of ways. There's not just one square root. There's a whole bunch of square roots. So this kind of speaks to your question from earlier as well. Depending on what the graph is, you could have a zillion square roots if it happens to have a lot of different involutions. Each involution is exactly one of the square roots. Or there are some graphs where no, it's exactly one, and this is what it is. And that has to do with what kinds of automorphisms the graph admits, or how the degrees are, all kinds of sort of independently interesting graph structures. So you guys seem to be 100% on board with square roots, or 100% on board? Okay. So it's October, switchy season. Which graphs are squares? Which graphs are not squares? Which traits make a graph square? So these are the questions that are interesting to a mathematician like myself, and hopefully like many of you. And the folks that were looking at this before had a different list of questions, which they answered beautifully, but they didn't think about these questions. And so it's kind of like we're starting from scratch here. So the second group of folks that I started working with at AIM, I've just been thinking about, okay, well, how can we measure this? So we've got this formal involution definition, but there should be something about like, the components of a graph, or something that's sort of an ordinary graphy way of talking about stuff. And so that's what we were curious about locating. And it turns out you can answer a lot of different ways for these questions. And there's all kinds of stuff that kind of pops out that's a little bit surprising. So these guys, all squares. You can prove that they're squares. Even cycles are squares. Well, we saw C4, it turns out C6, C8. All those guys are squares. And for the same reason, remember for C4, we had like an L and then we put two L's together. So if you wanted to do C8, you would take a C and put two C's together. So basically you have a path with half the vertices and you say, do a jump rope and make the other path on the other side. There you go. Okay, so even cycle is pretty straightforward. What about odd paths? Anyone do that off the top of their heads?
Center vertex.
Middle vertex.
Yeah, center vertex, and then you kind of windshield wiper it over. You can see how thinking about it in kind of a structural way. It's a very natural thing to think about. A complete multipartite graph.
One part says the bottom.
That's not the one I'm thinking of. Let's see if that would work. Maybe that would work. No, it doesn't? Okay. No, that totally doesn't work.
No.
So this is where it starts to get a little screwy. So one thing that has to be true about like the wings is that they can't have any edges between them. And so you got to be real careful about that. And that on the one hand lets you prove stuff isn't a graph because there's no way to kind of split things up into components that don't have any cross edges. But sometimes also it gives you a clue as to what to do. So for example, often if you can find two vertices that are not neighbors of each other, but have similar neighborhoods, that's a really handy thing when you're trying to find a square root. So as you start breaking down graphs in this way, you start finding little tricks where it's like, oh, it's easy if I can find this structure. It's harder if I can find that structure. And that was the line of research we wanted to follow. Anyone want to take a stab at multipartite complete? Go for it.
All but one part, that's the bottom.
Oh, all but one part. That might work.
So.
Could be. Well, then wait, hang on. But then which? Yeah, and then you kind of split up the other part into two halves. So that works if one of the parts has an even number of vertices. So this is the thing. So I only know the dumb, easy way to do it. But I believe there are many square roots. So one dumb, easy way to do it. If I just pick two vertices in the same part, what do I know about those two vertices? I know they don't have an edge between them. And I also know that they have the same neighborhood because it's complete multipartite, so they act the same. So I'll have these little wings on my butterfly that is just, each wing is just a single vertex. Each wing is just a single vertex. And then all the other stuff is the body. So that's not very natural, but it does satisfy the conditions. So another type of question, then you can kind of get greedy and be like, well, what's the best square root? Or what's the biggest square root? Or what's the smallest square root? There's a whole bunch of questions that I feel to a graph theorist are quite interesting that haven't been considered very much.
So then it's true then, graph with non-adjacent twins.
Exactly. Yeah, any graph with non-adjacent twins. Thank goodness that's already on archive. So you have not scooped us. But yeah, that's exactly an observation that's very helpful. It's really helpful to start looking for twin vertices that have something in common because that gives you a toehold into finding a square root. So I should mention, if you're curious about this stuff, so there's a paper on archive that's going to be EJC at some point. I think we're still like, there's one permission that needs to be signed or something, but to appear. That's by me and Annie Raymond and Pranav Garg. And it's on archive. Some of this stuff is in there. And then the other one, I finished my edit of the draft last night, and then the 4 co-authors are all going to look at it for typos, and then that's going to go on archive shortly. So if you're curious about reading some of this, you can keep an eye out or just ask me to email it to you. Yeah, so multipartite graphs. So there's a lot of square roots, and they kind of feel different, and it's an interesting thing. I'm not going to walk through the proofs of these other guys. So fun activity for you. So wheel graph is the, cycle with an added vertex and then spokes. So those guys are good. I should have said even wheel graphs. I'm sorry. And then this last bullet point I find fascinating because it's so different from regular numbers. So if I take 9 and I multiply it by 7, I do not get a square. But if I take a square graph and a graph that's not a square, and I multiply them, now I said product because I mean the Cartesian product and the direct product and the lexicographic. We have separate proofs for all the kinds of products there are, basically. And the join. If you've got at least one of them's a square, you're golden. So yeah, a lot of squares, a lot of interesting properties. Questions on this list?
The last one, is it like you take the square root and then you multiply?
Yeah, so typically what you can do is take the square root of the guy that's a square and do whatever your product was, but not always. Sometimes you gotta be a little finesse. Do a little finesse. Yeah, so that's what's kind of weird. So like with a lexicographic one, you have to do 2 separate proofs because it doesn't commute and the argument is different. But that's pretty cool, I think. There are some graphs where that's the unique square root, and others where no, you could also come up with something else in the product. So stuff happens. All right, so these are squares. What did we find any non-squares? Why, yes, we did. So these guys are all not squares, and so you can prove that no matter what you do, no such butterfly exists, and that obviously tends to be harder, right? Because you're showing something can't happen. There's a lot of proofs by contradiction here, and there's a lot of proofs relying on translating the square graph into something that's a graph structure. So this twins idea of 2 vertices with the same neighborhood, not quite an if and only if, but like kind of, you can jiggle it around a little bit and get there. So
essentially the gluing operation, you can glue across any subgraph.
That's right. You can glue across any subgraph, and that's why it's quite a large search space then to confirm that something's not a square.
Sorry.
Yes.
Surely, probabilistically speaking, you'd expect that every graph is like almost surely graphs are not squares. Because most graphs, like
just the count?
most graphs are asymmetric.
Perhaps I'm thinking through. I think
I'm saying a graph has trivial automorphism group. If,
yeah.
Well, and
yes, so it's unusual to have any sort of automorphism. I agree. The other subtlety with thinking about it probabilistically, which I think would be super interesting, is that you additionally have the layer of labeling. So would you want to make an argument about random labeling? Does that balance? So if I want to count how many square roots there are of graphs of this size, some of the graphs have quite a large number of square roots and some of them don't. I don't know how
I'm saying, like the expected number of square roots that exist.
Yeah, something like that could be.
Right. But like simply speaking, as in if a graph, we've said already that a graph is a square if and only if it has a butterfly automorphism.
Right.
And so if most graphs are asymmetric, then
yes, I agree with you.
Most graphs are non-square.
So kind of an unusual feature of a graph. I think it's still interesting to look at this list because humans like symmetric graphs, right? So a lot of the graphs that people are curious about go in there.
Natural examples.
If you wanted to take a probabilistic approach, sorry, I've like totally detoured to talking to the Zoom. If you wanted to take a probabilistic approach, I think what would be interesting would be, like you said, the expected number of square roots, because there is this peculiar phenomenon as well that some graphs have like a bajillion. And then I don't know how that would interact.
Yeah, okay.
Cool. Or to restrict it to graphs that contain some automorphism. And within that set, how many of them have this type? I would also like to talk further with you about this, but I'm going to hold it in. Okay, so these guys are not squares. A lot of the time you can come up with a proof by contradiction. We're like, okay, if it was a square, then there would have to be one vertex that is fixed by the involution, but then it would have to neighbor some vertex that's not fixed by the involution. And then, so you kind of go down this rabbit hole of if-thens until you find a contradiction. And so, for example, this circulant graph thing, if the relative sizes of, so circulant graph, you have n vertices and you connect them like every d, say. So if n and d have certain relative size conditions satisfied, then the circulant is not a square. The best proof we found after a year has 3 very painful cases, and each of them you separately do a by-contradiction in order to get that there's no such involution. On the other hand, complete graphs walk in the park, because if you had an involution, remember we talked about this, the left wing and the right wing can't have any edges between them. There are no vertices that don't have an edge between them in a complete graph. We're done. So this is also kind of fun because then if you think about complete multipartite graph, you're like, oh, that only works if one of the parts has at least 2 vertices in it. So if you start walking through these proofs or just doing some doodles, you start to notice what types of contradictions appear. The other result I want to point out here, because we were talking about products. So we know one direction is clear for pretty much any type of graph product. It seems so far, if one of the graphs is a square, it just kind of passes through and you're golden. It's open going the backwards direction. So there are non-square graphs that when you take their product, you get a non-square graph under these different types of products. And we don't know if it's if and only if, or that only happens sometimes. For a join, we have an if and only if condition. So if I take the join of 2 graphs and one of them is a square, it's definitely a square. If I take a join of 2 graphs and they're not squares, it's not going to be a square unless they have one very specific symmetry, which we fully characterize. So we know exactly when the join of 2 graphs is and is not a square. But the other products we don't know. So that's another open question. Other non-square. All right. Oh, I'm doing all right for time. So what I want to do next is talk a little bit about sort of proof methods and like, what do you do apart from just testing every graph ever? And so remember that other question was, well, which traits like do this? Because the ones you would guess initially don't seem to work. So we have quite a few lemmas and theorems and observations, depending on how hard the proof was, talking about just in terms of the graph structure. So like this one's about a cut set. Cut set doesn't have to do with isomorphism. Okay, we say isomorphism later on, but you can think about it in terms of graph terms that we're already comfortable with. So if a connected graph G has a cut set, so that when you pull out that cut set, you have at least 2 isomorphic components, maybe you got a bunch of others, but 2 of them have to be isomorphic, then it's a square. And this is a if and only if. So if you think about a butterfly, you're like, oh yeah, remove the body. I've now cut the graph and I have 2 wings that match each other. So that's the vibe of this theorem. But now we're talking about cut sets. You might know more about a graph's cut sets than you do about its involutions in general. So this is a real handy thing.
So did you say it can have other components?
Yes. Yes.
They're different?
Yes, because what you do is just get so grisly. Let's see, is this a good example? This is a better example. Okay, so in this one, for pretend, I could say the body that's in black, that's my cut set that I'm guaranteed. Okay, so if I look on the right-hand side, if I remove the body, well, I've got a couple of components. I've got like the big wings, I've got the antennas, I've got the tails. And it's enough just to have the big wings match each other. I don't need to worry about the antennas and the tails. And the reason for that is when I want to find a square root, I can just use a big square root. So I can say my square root is going to have both antennas, it's going to have both tails, but it's going to be missing that wing. And then it's okay. So this cut set thing is not necessarily going to describe every square root, but if a graph has a square root, one of them will be of this form at least. So it is an if and only if, but it does not describe every square root. So this, for example, if I'm curious about a tree, this is super helpful because I know about cut sets on trees. I am comfortable there. And that's actually how we came across this theorem, is by thinking about what could I say about a tree? And they're like, oh, actually, it doesn't have to be a tree. So this is handy. Questions on this guy? I kind of hand wave through the proof, which I'm hoping is obvious. Good, because that was the other goal, right? Is to be like, what are you talking about? Oh, everything is trivial. Okay, so here's another everything is trivial one. Oh, so here's the proof, but this is exactly what I said with my hands. So here's another trivial one. So both of these, by the way, are in that paper that's gonna be on archive, I don't know, in 2 days. No vertex chromatic critical graph is a square. If I already happen to know an interesting fact about my graph, which is if I remove any vertex from my graph, its chromatic number decreases. Then I know my graph is not a square. I don't need to do anything more. My work here is done. So proving a graph is vertex chromatic critical is a pain in the neck. That's as difficult or more difficult than proving it's a square. But there are many classes of graph you're like, oh, I have that for free anyway. Now I have a one-line proof that it's not a square. How wonderful. So for example, odd cycles. You could do the by contradiction, imagine this, imagine that, very lengthy proof, or you could say, if I remove a vertex of an odd cycle, its chromatic number goes down, not a square, done. So that's what these theorems and lemmas are useful for, letting you use knowledge you already have about a graph to attack it on the square side of things. Why is this true? Well, so say for pretend I have a square, then all I got to do is color the body of the butterfly and both wings the way I would have colored the original square root, and I'm done. Trivial? Yeah, okay, good. So a lot of the work is this kind of thing where we're like, okay, what's something I already know about graphs? Can I translate it so that it comes in handy? I think this is super cool because, like I said, this really disgusting proof of odd cycles, which you can recreate on your own if you want, becomes one line. So we have several other results like this in the paper to appear, but those are the ones I thought were good for this group in this session. So I believe that's it for the conditions I was going to highlight. Questions, comments? Okay. What the next slide is? Oh yeah, motivation. So usually you put the motivation at the beginning, but I figure we all love squares, right? We're all curious about C4, so I'm going to start with that. But this does actually have a motivation. So I went to a talk over the summer where someone asked the speaker about motivation. And they said, well, if you don't care about truth and beauty, and I'm like, yes, this is always my motivation, truth and beauty. So that's the perspective I came at it on. Honestly, I like graphs a lot. I like breaking them apart and putting them back together. And I didn't need to be more motivated than that. Truth and beauty. And a lot of the results that we've got are just kind of like, oh, what a weird thing. That chromatic number is popping up over here. Oh, it's true and beautiful. But there is also another motivation if you want another motivation. So the folks that kind of got me into this were curious about Sidorenko's conjecture and homomorphism densities and whatnot. Okay, so Sidorenko's conjecture, very famous. I cut and pasted this from Wikipedia. I'm going to assume that we all know as much as we want to know about it already. So it's saying this number is bigger than that number. But another way to phrase it is to say, oh, if I subtract them, it's bigger than 0. So often when you're reading it on Wikipedia, you'll have like a hom in there or a t, or there's some indication that's a function of the graph. So what these guys observed is that you don't need the function. The behavior of this gluing algebra is the same as the behavior of the density. So we could just mess around in the gluing algebra and for free get all this homomorphism stuff, which is amazing. And all kinds of cool stuff has happened because of that. For example, here's a complete proof of Sidorenko's conjecture for a path on 2 edges. Oh, this is the same formula I showed you at the beginning, right? So look, if I have 2 edges together, and I subtract 2 separate edges, it's a square. You can see all the way on the left, so it must be positive. Squares are always positive. So this difference must be positive, therefore the inequality holds. Zoom people are making amazed faces. So this is an amazing motivation. I think this is really cool. So folks that are really motivated by this want to hit all kinds of Sidorenko relevant or other homomorphism density conjecture relevant graphs with this hammer, because amazing. So if you take, so one thing that I did with Annie and Pranav was to look at, okay, some extremely sophisticated folks have given an extremely sophisticated proof that this class of graphs satisfies Sidorenko's conjecture. Is it also square? Because if it is, that gives the hope that we could come up with some clever polynomial thing instead. So does it admit this kind of square polynomial type of argument? And so we were focused on graphs that are interesting to those guys, which is a reasonable way to approach it. And so we figured out that a lot of the graphs that have these very complex proofs for satisfying Sidorenko's conjecture, in theory, you could also write a proof like this. So it turns out if a graph has a square root, then it may have a polynomial expression like this that would do what you want. Now, the problem is it's not just like take the square root. It has to be a very complex series of sums and products so that everything cancels in the way you want. This one happens to cancel real nice, but there's other situations where it doesn't cancel nice at all. But what these other folks proved is that at least the leading term has got to be a square for this to ever work. And so if I know that my initial graph is a square, I can be like, okay, maybe this is a worthwhile method. If I know that the graph I'm starting with is not a square, then I'm like, this method's never going to work. I'm walking away. So that was our earlier contribution. So if you look at the paper that's actually public, it does similar types of arguments about does it have a square root or not for these very abstruse graphs. And the reason we're doing these very abstruse graphs is because those are the ones that are relevant to the Sidorenko's conjecture. So there's that chunk of work with that motivation. And then, of course, there's a lot of other conjectures out there, right? And there's some partial results on those, or maybe you could do. So this technique is super powerful and gives you classes of graphs that are of interest because of their relation to the conjecture rather than because of them just being true and beautiful. So truth and beauty is one motivation, and doing something super cool with homomorphism density is another motivation. I hope you guys are motivated by at least one of them. It's a really nifty technique. I'm not sure what's on my next slide, so maybe I'll pause and see if there's questions about this slide before I proceed. All right. Oh, and that's the end. I didn't even make a thank you slide. Well, so there we go. Thank you so much for your attention. I love talking about this stuff.
Any questions? On Zoom, any questions?
No, I got a head shake now. Yes.
A little bit more connection between the squares and the homomorphism.
Yeah. A little bit more, but not a lot bit more. Because like I said, I'm the graph person. I'm not the homomorphism person in the team.
Is that product the?
Yeah, so this one here, I'm going to be using the gluing algebra. So what I want to show is the graph that I care about, whatever it is bigger than if I just took, then I wrote K2 because that's like a single edge, right?
Yeah.
So if I just had that many disjoint edges, the same number of edges that I'm subtracting as our edges in G to begin with. So that's Sidorenko's conjecture. Homomorphism does. Yeah. So again, Wikipedia. So that's the idea is the original conjecture is saying G is greater than take a bunch of separate edges. In the sense that if you take the homomorphism density in a random graph, blah, 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 blah. Okay. So the original conjecture had imagine that the subtracted thing over on the right-hand side. So G is greater than this. But we know how algebra works. And we know that this is an algebra that we're working in right now, this gluing algebra, which is not necessarily a feature of other types of products. So we are allowed to subtract. It works fine. So subtract it to the other side. So this is an equivalent statement of that homomorphism inequality of Sidorenko. And what's great about it is now we want to show something's positive. And if something's a square, because of the special properties of the algebra that other people have proved, it's positive. So that's the point. So suddenly we have a tool of like, oh, if I could show that this polynomial has a square root, then I'm golden because now I know it's a square. And sometimes you can do it very directly. So this is the best one, basically, that those folks have found because it all fits in one line. One expression, you square it. Hello, Joshua. I'll finish saying this and then I'll see
Yeah, I wasn't trying to.
So you take this expression, you square it. At that point, we know it's going to be some cockamamie graph polynomial, but it's going to be positive. Then you group like terms and do all that stuff, and you happen to get the exact graph polynomial that we wanted, which was the graph of interest on one side. Oh, I should have used H before, I'm sorry. So graph of interest, subtract just a bunch of edges, but it's the same number of edges as in the original graph of interest.
Being that when you can take a graph and write it as like
Yeah.
square root where like you have this minus how
Yeah.
many edges, then you can.
Then you're all set. And so if you look at some of the papers by Blekherman, Raymond, Singh, and Thomas, you'll see like a page-long series of okay, this squared plus this squared, and then I cancel this, and then I add this squared on. So they become very elaborate, but it's the same basic idea of like I'm going to factor in quotes a graph polynomial so that it's a sum of squares. And then that tells me positivity, which is what I actually want.
Thank you.
But there's no canonical way to do that, which those guys have been thinking about for whatever it is, 7 years. I've been thinking about for 2 years. There's no canonical way, so you just have to hit it with a hammer or come up with some better approach.
So all squares satisfy Siddle-Ehlers conjunction.
No, so that's a little too strong. I'm so sorry. So what is known is if there is some sort of sum of squares argument that you could make. So maybe you glue together a few terms that are squares and so forth, and at the end you get the simple expression you want. Then the left-hand term in the simple expression you want must have had a square root earlier on. But even if you know it has a square root, that still doesn't tell you how to combine it with other things and make the argument. And it's possible that there's no way to combine it with other things and make the argument, even though that one has a square root. You also need to do this canceling. See how this like kind of canceled in the middle? And that may or may not occur, or maybe it'll occur only if you subtract the right thing and no one will tell you what the right thing is. You have to just do an exhaustive search. But it does tell you if there's no square root for the thing on the left, don't even bother. You can quit now and find another method. So that's the amount of knowledge we've got right now. Thanks for waiting.
No worries. Rather unrelated. Well, no, sorry. Question on the topic, but unrelated to the things we've just been discussing. So if you take the automorphisms which characterize being a square, so like say like the group, like the butterfly automorphisms, whatever, those form a group. And have you considered this and how like you could read information from the group about this, like the different automorphisms that exist? You're just saying, oh, the largest ones or the smallest ones in terms of the body you're fixing, or can you even learn information by like viewing the graph or the cycle space of the graph as a representation of the butterfly automorphism group? And have you thought about any of those sorts of things?
The answer is no. I have not thought about any of those sorts of things. I think some of them, if you think about it or if I think about it, might be pretty quick dead ends, but others might not. I tend not to think about the automorphism group in isolation. So yeah, no is the answer. Nobody I know has thought about this. And that sounds like a good thing to think about. Other stuff in the room, out of the room.
So how do I understand this? So is it correct that there is a way in including algebra to define one that's
Yes.
And then at the end of this, and then one way to show this, that inequality is to show that something is a square.
Yes. Yes.
And then at the end, we want to do that. We need two graphs. One
Yes.
graph is power of eight. The
Yes.
other graph is y.
Yes.
And what's that happens then this graph satisfies.
Yes, that's correct.
So I think this condition seems very strong to me because we want to be in two graphs where one graph is the power of two.
Yes.
So how open does it happen?
Yeah, well, so not that often so far, I suppose. So this specific type of equation has not been the thing that I've been looking at so much, but I know where to find it. So there's a paper which I didn't give a precise reference, but search on archive. So it's the list of authors that I mentioned up here. So that's a paper that has some explicit, okay, so this paper has explicitly lays out this sort of groundwork of like, okay, look at the gluing algebra. Then it satisfies these conditions in terms of sums canceling. It satisfies these conditions in terms of inequalities behaving the way we want. And I will now use it to demonstrate some already known Siderenko graphs, but they tend to be quite small indeed, because it's quite difficult to find that chain in the middle that demonstrates and cancels. So if you're curious about that kind of question, I think this is probably your best place to get an answer, because it has several examples that have that chain of cancellation. And I think it also discusses how super hard it is to find more examples, but maybe your brain is good at doing that. I know my brain is bad at it. Finding that chain of cancellations is quite challenging. Which is why I looked at other stuff.
Other questions? All right.
That was really nice.
All right. Thanks, everyone. I'm going to end the Zoom now. All right. Bye.